Good day, everyone. Um, Thanks for your time. Okay. I did make a post yesterday. I think, yeah, about a three-phase horizontal separator and how to about the mechanical drawing and how to model. That I was going to do a modeling of the horizontal separator based on the mechanical drawing that I also shared. Well, this was because for some time now, some persons have reached out to me in one way or the other via WhatsApp and as well as on LinkedIn. Wanted me to at least show some demonstration on how they can get started with modeling a vessel. I think some persons have asked because they got stuck along the way, and after trying, and they actually couldn't find what they were looking for, so they had to just ask that I guide and then help to direct them on how they can get familiarized with it. So I decided to do this demonstration so that it solves the problem of those that have been asking, that have asked me to do the demonstration earlier, and those that just asked me recently, so that if they could get their hands on the video of this demonstration, it would be able to solve the challenges or whatever questions they need to be answered. So that's why I'm doing this demonstration, and I'm going to see as fast as I can touch this mechanical drawing and help them understand or get a better understanding of it. So let's move on. What I have on my screen is a mechanical drawing. It's a bit different from what I posted in what I used in the post that I made, because there were some things that were not complete there, and there were also some things that were not supposed to be. So I had fine-tuned the mechanical drawing and I came up with this. However, this is also not 100% perfect. I've just tried to put up this for the sake of this demonstration. Yeah. So would hope that we wouldn't have any hitch trying to work with this document. But along the line, if we have any, I would explain, and then we'll see how we can circumvent it. So this is a 48 inch by 10 feet turn to turn three-phase separator. Yeah. When you say turn to turn, it means, if you can look at my screen, it means from the beginning of this shell to the end of the other shell. That is turn to turn. And some drawings would say S to SS, which is seam to seam. It's the same thing, and the same from one end to the other. Like in this case, we have 0 to 30 points. 30.48 meters. So that's 3,048 meters. So that's the length in millimeters, as well as the diameter also is in 48 inches. It's usually written in inches, and then is along the line you convert to whatever you'd be using. So we have this drawing. This is the side view, this is the front view, and then this the nozzle schedule. Also in this nozzle schedule I had some little changes that were made. Yeah. were some little changes that were made. Okay, so it may also not be perfect, but along the line we'll look at it. Then we'll have the saddle details. That's the detail of this saddle. This saddle detail would only be working with the length and the height and the length of the base, because the other details are just for fabrication. So let's dive in. This is a vessel that has quite a lot of nozzles, as well as manway and a saddle. So the nozzle schedule has been outlined here, the rating, the type, which is a race face, as well as the outside distance. This is actually the projection of the nozzle. Some nozzles are projected more from the vessel, while others are not. So, and these are also inside projection. What you also have here is weld details. This is actually what the welding engineer would be interpreting for fabrication. So we'll not really be going into all of this. What we'll be just focusing is on the vessel, drawing the 2D, drawing showing the front and the side view, the nozzle schedule, and the saddle details. So we'll be interfacing between this and the software to get information and as well move on. So that's it. Let's go straight to the software. So I'm using AutoCAD Plan 3D, which is my basic software that I use in process piping designs and every other activity. So I've created a project. I created this project as using the option of mixed, which is imperial and metric, and it just helps, it makes it more flexible, so you're not limited to either of the dimensions. So I presume all of those has been done, and this interface also, I presume, before we get to this stage, we must have understood what the interface is. So I will not be speaking about those. I'm just going straight to the design. So I've created a drawing and I'm opening it. This is what it is. So this is a blank drawing. We don't have anything. So to begin, I go straight to my tab, home tab, and then equipment tab. AutoCAD has been able to give us quite a lot of equipment that we can work with, but we're going to a vessel and then a horizontal vessel, which is what we'll have. Now, I tried doing a little demonstration before this video, so some of the information that I had used for the demonstration while I was testing the mechanical drawing, because I needed to test it to be sure that it's workable. So I still have some information that would now be left in the memory of the software. So while we were working, there are some places that I wouldn't need to impute. I will just explain because I had already imputed them, so you'll just be seeing them on the screen like pre-populated. But however, if you're working, if once you select your vessel, the system automatically generates the thorispheric head, generates the cylinder, and generates the other thorispheric head. You know, as horizontal vessel, it has two dish ends, one head the other side and the other end at the opposite side. And again, typically the cylinder must have its saddle, so that's why you're seeing this saddle under the cylinder. Yeah, the saddle are like the legs, and since this is a horizontal vessel, it has saddles. Vertical vessels come with skirts rather. So if it's for a vertical vessel, what you'll be seeing here is a skirt, or in some cases you have legs, which are like tripods, or in some cases 4 legs or more. But in this case, we are just dealing with a horizontal vessel, which has to do with saddle. So these are what we'll be editing based on that drawing that we've seen before we now start imputing their nozzles. Okay, so let's now let's include. Okay, so cylinder. For the cylinder, we have to impute the diameter of this, which is given here as D, and the height, which is given as H. The system has been built in a way that once you can determine the diameter of this, that same diameter will automatically be assigned to the heads, the dish ends. So if you like, you use 60-inch, the terrestrial head will change to 60-inch. If you put the diameter here as 24-inch, the terrestrial head will be changed to 24-inch. That's how easy the software has made our job look. So and in this case, in most cases when I'm doing this, I use a calculator, because the calculator helps me to convert easily and then get what I want. So we are using the calculator and want to impute the diameter of this vessel. So if you go to our drawing, you see that this is the dimension of the vessel that was given. Usually it comes in this way. Diameter is usually of the first before you see the length. Diameter is in inch while length is in feet. So once you see this, you should understand that this is a 48-inch diameter by 10 feet length of vessel. So 48-inch is what we'll be converting in our calculator. So it said 48. Once we input a 48-inch there, it will convert it directly to millimeter, because what we are working with here is in millimeter. So you are having 1219.2. I told you I've done this before, so it's like this is already in the memory of the system, of the software. So if you've not done it, you can input your own value here, 1219.2. Now the next thing we are looking at is the length, which in the software is called a height. So convert this to feet. This is how I do it, and I put 10 feet. 10 feet is giving me 30.048 and 3.048 meters. So that's just 30,048. So 3,048 meters. So that's what you impute here. So once you've done this, the software automatically generates the other ones. You see the terrestrial head is having the same number both up and down. Now let's move to the saddle. Now I told you the saddle are the legs for each of these, the two legs that the vessel carries. Saddles are usually in pairs, especially for vessels like this, except in some rare cases which will not be discussed here, that you just have, it's usually in pairs. Let's not go there. And yeah, so that's basically what it is. So what we'll be starting with now is, let's look at the saddle height. The saddle height. This is telling us now that our height needs to be calculated from the middle of the vessel to the base of the saddle. That's what it's telling us. From the middle of the vessel to the base of the saddle. That is what the height is going to be. If we look at our design, we realize that this information is not how it was given. The way the software is requesting it is not how it was given in the design, but we'll have to figure it out. Now let's look at the drawing closely. What it's simply asking is that the height from this point down, looking at my mouse, to this bottom of the saddle. That's what it's asking. But what we're given here is just the height of the saddle from here to this point, meaning that we don't have the other ones. And we also see that somehow 200 have projected into this part of the vessel. So what we've left from this line now down to this place will have to be 600. So for us to get the total length, we now have to take half of this and add with the 600. That will now give us the total length, which is what the software is asking. So to do that, let's go back to our software, our calculator, convert back to inch. Half of the vessel will have to be 24. Since the total of the vessel is 48 inch, half of it will have to be 24. So let's look at what that 24 is in millimeters. 24 inch is giving us 609.6. So 609.6, we'll now have to add it with 600. So let's copy and go to standard calculator. Paste it, then add 600. We know where the 600 is coming from. The 600 is this other remaining part of this saddle, since 200 has already projected into the vessel. So the other 600 is what we'll now add. So as I was adding plus 600 equals 1209.6. So this is what our height is going to be. And like I said, I've done this before, so we're having it already pre-populated here, 1209.6. Now our length, which is L is, I want to follow this serially so we don't miss anyone. Our L is the distance between the tan and the middle of the saddle. That is our L. And in this case, we look at it, L is giving us, it was not given exactly the way the software. So one thing we would notice is that sometimes the software, the way the software is designed, would not be the same way the mechanical drawing is designed. So would have to look for a way to do plus and minus and addition and subtraction and be able to get what we want. So since we are only given from 500, from this point to this point, which is 500, we have to now look for the middle of this, so that once we add it to 500, we'll get what the software is asking for. Now, sorry, bear in mind that in the software, let me explain something. In the software, it was stated at the top, but in reality, what they use is below, as in is the base, not the top. So that's why if you look here, you see that it was at this point that the arrow came down to, else they would have used it somewhere here. So it's the base that is the reference, not the top. Understand? So what we are saying is simply that it is this 200 that we are looking for the middle, not the 300. So if we take half of this 200, which is the distance of the base, or the length of the base, which is 100, and add to this 500, we'll now get 600, and then we impute it in our software, 600. And our L2 is this length. Now if we look at our design, we realize that we do not have any base plates for this saddle, so meaning that in this case L2 is not applicable because we don't have anything. So that's why it's seen L2 as 0. Understand? Now our L3 is now the distance between this middle of the saddle to the middle of the other saddle. Now we'll go back to the software. We realize that there's something I want us to understand. Whatsoever, let me use the software rather. whatsoever you're having as our L here, once you impute it, the software will assign the same thing to this other side. Software will assign the same thing to the opposite side. Understand? So if we are having 600 here, that means this place will also be 600. So once we have that at the back of our mind, it will now be 600 plus 600, that is 1002. So for us to get the center to center of this, we have to minus 1002 from the total length of this vessel. To do that, we go back to our software. Our total length is 3048. So to remove 600 minus 600, it should be 12, so it should be minus 12 equals 1848. So this is going to be what our L3 will be, 1848. So L3, 1848. So we are progressing. Our T is now the thickness of the base plate. Initially, I've told you that we don't have a base plate, which is why we put 0 for L2. The same thing will be applicable here. We don't have, so T will be 0. Now I have W. W is the width of our saddle base. Yeah. So from our software, the width is 200. So that's why we're having 200 here. And then W1, which is, for trace, you see it's the top of the saddle. In this case, we are having it as 300. So the 300 we have here. And then W2. W2 is also that base plate that we don't have. So that's why we're still having it as 0. So at this point, we've been able to put in every thing that the software needs from us. And so we can create. Fine. Okay. I just noticed something. The vessel I created initially is still here. So what I will do is I will just remove all the nozzles and create them again, so that it's not confusing, or so that everybody would be able to follow. So just give me a few minutes. Let me delete them. Okay. 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 Sorry. I just want to have them deleted. So that we create a new one. And the last one. However, sometimes, not sometimes, always, once you create a vessel, the system automatically generates some nozzles for you. So you can modify, but in this case, I've just deleted both the ones that I created and the ones that the system created. So we will not be having any nozzle on the vessel until we start creating. So I want to explain something before we move. For these two dish ends, these thorispheric dish ends. One is usually considered the head, the top rather, and one is considered the bottom. If we look at our drawing, we realize that one part of it starts with 0 and the other part is the end. So you know that the system recognizes this part that starts with 0. The system recognizes this dish as the bottom, and this one that gets to the maximum length of the vessel is where the system considers as the top. Yeah, so would use that reference to help us know how to position nozzles. So having created a vessel, and then let's look at it closely. Fine, so everything looks fine now. So I want to create a vessel. So let's get to the software. The drawing rather. I want us to start with N1. N1 is this. If we look at our nozzle, see that N1 is 4-inch nozzle. Yeah, 600 pounds rating, raise face, 200 projection. So it's a 4-inch. So we create, right click, add nozzle. Now this nozzle, I've told you that it is at this side of this. So where you're having this is top, this is bottom. So I have to put this nozzle at the top on the software. So we choose here and we'll go to top. The nozzle comes here. So we'll do modification. Now it says radius. Radius, in other words, is usually the distance from here to where you have the center of the nozzle. That is the radius. If it's for the top, it's the distance from this reference to where you have this, or where you have this, or you have. So in this case, the radius here will be 510. In this case, the radius here will be 306, because the software sees a reference on the dish. It sees the reference from the tan, which is this. But for here, it sees the reference from the center line. Yeah, so it's either you reference it up or you reference it down. Yeah, so as we progress, we'll see that. So in this case, our reference for this nozzle is 306. So we input 306 here, 306. Then our length, as we've seen, says our length of which is the outside projection, is 200. So we go back there, we input 200, and then angle. This angle now is also what we'll be looking at. Now let's look at this. Let me explain, because once we pay good attention to this place, it will guide us. Let me put this in 3D dimension so that we can easily see what we are doing with the nozzle. Okay, so if we look at this now, we realize that this nozzle is, in this case, at our right. And then if we look at this, we realize that it's somewhere here, which means it is at 0, and it shouldn't be. We should have it up, which is at 90. So this is going to be our angle. So we go back now. We hold our control key using Windows control key, and then click on the mouse on the nozzle and click on the pencil key to take us back to where we'll modify the nozzle. So We are changing the location. So this is place we are putting 90. Like I said, 90 is top. So if you look at it, you see that it has gone up. You can now see that the nozzle is now at the top. Okay. Yeah. So you can view it this way, just like it's appearing on the mechanical drawing. So next is the nozzles. So like I told you, it takes a reference. Want to deal with the nozzles at the top, so we'll be referencing from here, which is the bottom. And then we'll do all the nozzles. I will do a few at the top on your own. So I'll just show you how we do the two first, and then how we did the other ones below. Yeah. So now let's go. The first nozzle is N5, and I want to start here because it's easier. Yeah. So this is N5. It's 510. N5 is 2-inch nozzle. Every other thing is the same, but the projection is 150. And then distance is, the radius R is 510. So we'll now go here, right click, add nozzle. So now this nozzle is radial. It's nice, it's okay. If had it been wanted it at the other ends, it would have been either top or bottom. But now we want it at the dish, so it's radial. That means it's correct. The length is 510, just like I showed you in the diagram. The drawing is 510. So we impute the height, in this case 510, which is the distance. The length is its projection, outside projection, is 150, and the angle has to be 90 because it's at the top. So bear in mind it's 90. So we'll modify the type of nozzle. 4-inch nozzle, 600 pounds, straight nozzle, and then it's 2-inch. Okay. So the next nozzle would also be radial as well. So what we are doing now is, that is N4. I now have to add 639 to 500 for us to get the distance. So 510 rather, 639, adding to 510. So 510 plus 639, 1149. 1149. So that's what we are adding here. 1149. Yeah. The length is, that is the projection for N4 is 150 as well, and it's a 6-inch. So sorry, I think there is a mistake. Let's redo that. This is 90. This is 150. This is 1. What did we get here? 1149. 1149. Yeah, so we move to the type. is a 6-inch, 600 pounds, and his raised face close. So I've done these two. I would go down and do these other two that will have below, these other two that will have below, then do the man way. The other ones can be done later. So the same thing, go here, add nozzle. This time around, it's still a 2-inch nozzle, which is N10. N10 is still a 2-inch nozzle, 600, 150. So this is the distance there we saw is 45. Is actually, the center. From the center to this is 45, which by standard is not right, but I just trying to demonstrate. Yeah, just trying to demonstrate 45. And length is 150. Then this time we have it below, and below is 270. So we put 270. It has come down. We change it to 2-inch. It's a 2-inch and 600 pounds raised face. So we close, and then let me generate the last one that I said I will. Other ones you can practice and generate yourself. So add nozzle, and so that's one now is N9. N9 is 4-inch, still 150. So, and then the length or the distance is 240 from the tan. So this is 240. 240 is still 150. Is still 270. I go here. It's 4-inch, 600 pounds. So we'll close. If we look, you see that both of them are clashing. I'm just doing this for this sake. Else, we can still modify. Can just increase. Can just increase this, even though it's not on the. It's not what you have on the drawing. Can just increase the distance of this to 300. Okay. Yeah. So it gives it a little. It gives it a little gap. So I've done these two nozzles at the top, done two below. We can try to do the rest, but before that, I want to also do the man way. So if we look at this drawing like this now, we'll see that we have this. We'll now have it looking like this. We'll now have it looking like this. We have the nozzle here. We have this. We've not done this. You do this on your own. So what we want to add is the man way. Now, if we look closely, we'll see that these ones are by the side. Unlike this one that will have top and bottom, we'll have by the side. So it's either 0 degree or 180. Now our man way is at the left hand side, which means it's 180. At 180 that we'll be having it. And our man way is also at a distance of 2 meter 48. Yeah. So 2 meter 48, which is our man way N17, is 24-inch man way 30. That is the projection outside, which I believe is an error. It's supposed to be 300. So let's go now. Let's create a man way. we click here and we add nozzle. Yeah, so it's creating this nozzle at the right hand side. Meanwhile, from our drawing, we need it at the left hand side, so we change our angle here to 180. Yeah, it has gone to this other side, and we change our length to 300. Okay. And our height, we leave it at where it is. Yeah, because we just need it to be centered. Okay, no, our height rather, sorry. Our height, which is the distance from 0 is, what is our height? Our height from here, our distance 2 meter 48. So we impute 2048. Okay. Now we change this type. What type is this? This is a manway. So we choose manway here. It's a 24-inch manway. Pressure class does not really matter. Manways are designed in a way that they are massive. So diameter is not oval, it's round. So we just choose this and we close. So we have the manway now. And it's okay. So this is how it is. Yeah. So the next thing on the last part of it now is what I want to create is the other nozzles at the right hand side, like the bridle nozzles and every other thing, which are these nozzles that we have here. These nozzles, these are 0. So we'll go back and we create. So I want us to start with this first nozzle, which is N11. Yeah, N11. And then we can now go with the other. So this is N11. And N11 from here is a 2-inch nozzle, 200 length. So we create it. But the distance is, this is 800 and this is 250. So that is 1 meter 50. That is the distance. So we have 1050. The length is 200 projection. That's what we have, and it's good at 0. So we change it to 2-inch, 600 pounds. Select it. We are good to go. We'll close. Yeah. So we are not done. Now if you look, you see that it's at the middle, right? So we, from the drawing, it's supposed to be at a distance from the middle. So we have to go back and modify and impute 186. Yeah, we have to impute 186. So come back, we go again to the software, the nozzle control, select it. Yeah, so go back to changing the location. We'll have this, then we'll have the 0. 0 is now the offset from here to where we need it to be. Yeah, so that's the 0. So from here, what we have is 186. So we input 186 here, 186, and it goes up. Okay, so create the next nozzle. We use that one to do what I wanted to demonstrate. So can add nozzle again. Yeah, so Want to create the second one, which is N12. N12 is still the same, 2-inch, 250. So, and then we'll create it the same distance of 1050. Yeah, that is this is 150. Sorry, this is 200. So it's now for us to impute what this will be. So looking at this, it's 460. You know, the other one was 180. Now this is 460 away from the middle. So at 460, what we will do now is, instead of imputing 460, we'll make it negative. We'll put minus 460. You see that it comes to the bottom. Yeah. So minus, once you add minus, it brings it down. So we can change this type. It's 2-inch, 600 pounds. Raise face. So we'll close. Now we've been able to generate these two. Yeah. For it. So let me do one more, and then I'll allow you do the rest. So let's do N14. N14. Yeah. So N14 is also a 2-inch, 200. So it's just almost the same with this one we've created. And the distance is just 250. So we click here. We create another nozzle again. The height here is 250. Okay, this is 200. So this is 200. The angle will now have to be, what are we seeing here? Is 255. I'm looking at N14, 255. So just like we did, it's still 0. It's still this side. So we are putting minus 255. Yeah, so it's bringing it down here. So now just change the size to 2-inch, pressure class to 600. We are good to go. Okay, so we have quite some others that you can create. Okay, I want to create one that is not a normal raised face flange, so that we can also demonstrate with that for you. I can also demonstrate that for you. So we have this N16. N16 here is not a raised face flange. So the distance is 542, and it is a 3/4 MPT, 3/4. So it is 520, 520. The length is 50. So let's look at this. That is N16 rather. Okay, 3/4. And then it's 283. So this is 283. That's the offset. They will change it. It's not a flanged, it's a threaded female. It's threaded female. It's 3/4 and it's 3,000. I want to use 6,000 rated. So that's it. And we close. So I've been able to do quite a number of them. So you can just practice with the others that we have based on how I've done this demonstration. I believe that before you do these other nozzles that will have these three below, and then these other two we have at the top, they will still have N15 here. You will be able to figure this yourself. And we still have N13 here. So by the time you're done with that, at least you would have practiced a little. Now, mind you, if you look at this drawing, you'd see that we still have two dotted lines. These are internals. Yeah, that's why I have them in broken line. Just like I used to say, for you to dive into this, you must have basic understanding of oil and gas. You must have basic understanding of oil and gas vessels. You'd have read about them. You should know that when you have a wear, you should not interpret this because it's a dotted line as this. Any designer would know that this is a manway that they're seen from the other side. And this is an inlet diverter and this is a weir. So these two are inside the vessel. I just use this to show. This is for fabrication. So those that are fabricating knows that this is the distance where the weir would be. And this is also an inlet diverter. Details of this was not actually given, but in recent details of it is usually given. So, well, this is the demonstration I promised. I think this is fair enough. This, was useful. Yeah. So, thank you everyone for your time. Thank you.